Hi students, myself Satish Kumar. In this video lecture, I'm going to present the analysis of n isotropic sources which are excited with currents of equal amplitude and equal spacing, and we are also excited with currents of equal phase also. Okay, so that means it is nothing but the broadside case of an n element array. Simply speaking, it is the broadside case of an n element array where we are keeping all the elements which are equal in spacing, let's say that is d, and they are excited with currents of equal amplitude and equal phase. Okay, the phase difference between them is zero. Okay, so let us try to see the analysis. An array is said to be broadside array if the phase angle is such that it makes the maximum radiation perpendicular to the line of array axis. This is what we said in types of arrays lecture. Okay, a broadside array is the one in which the elements are equally spaced and they're excited with currents of equal amplitude and phase, and then it fires its radiation perpendicular to the array axis. If you take the x-axis is theta equal to 0, okay, and if the array axis is along that x-axis, then it fires in perpendicular direction, which is 90 and 270 degrees. That means the major lobes, it's a bidirectional radiation pattern. One major lobe will be along 90 degrees and other major lobe will be along 270 degrees. Okay, this is what is the general thing that we have already observed in two element array. Okay, now let us see how we can do the complete analysis. Here, analysis actually means we are going to find out the expressions of different angles through which we can able to draw the radiation pattern for any element array. If n equal to 3, we can just substitute n equal to 3 and we can get the angles and we can able to draw the radiation pattern. Similarly, if n equal to 4, if n equal to 6, n equal to 8, just by substituting the value of small n, which is the number of isotropic sources in that antenna array, we can able to find out the angles, different angles. Which angles are those? I'm going to tell you now. We'll find out those angles and we can able to draw the rough radiation pattern. This is what we are going to call it as the analysis of n isotropic point sources of a broadside array case. First thing, in broadside array case, the sources are in phase. This is what I said already. Those sources are in phase means the phase difference between them is zero. This alpha is the extra phase difference, which is always equal to zero. And for the maximum radiation, okay, we will be considering psi is also equal to zero. I said psi is the general phase difference between the two element array. But for n element array, we will be considering that psi is also equal to zero. And in the analysis of 2-point arrays, we already came to know that psi is equal to beta d cos theta plus alpha. Okay, beta d cos theta is the general phase difference and this alpha is the extra phase difference that we will be giving at the time of excitation. But this extra phase difference alpha, which will be equal to 0 because all the elements are in phase with each other. Okay, so then you will be taking that alpha is equal to 0 and psi is equal to beta d cos theta. But we are also considering psi is equal to 0 here, so that psi is equal to beta d cos theta is equal to 0. Then cos theta equal to 0 by beta d and cos theta is equal to 0. Then theta will be equal to cos inverse of 0. You will be absolutely getting equal to 90 degrees and 270 degrees. This is nothing but the theta maxima of major lobes. Okay, this is the first angle that we will be finding, and this is also called principal maxima. Okay, so these 90 degrees and 270 degrees, in this the principal maxima occurs in these directions. That means these are nothing but the major lobe maxima directions. Okay, so directly we will be finding out this. Even if we don't find also, we will be very clearly indicating that the case itself is a broadside array case, and as we know from the types of arrays itself, we will be considering that it fires perpendicular to the array axis. Those angles will be obviously 90 degrees and 270 degrees. Either you can directly take the maxima of major lobes is 90 and 270, or else you can, by equating psi equal to 0, you can get those values. Next, what are the other angles that we are going to find out here? Okay, the other angles that we have to find out are pattern maxima. Okay, don't consider that this pattern maxima is the maxima of major lobe. These are the maxima of minor lobes. Okay, I'll be giving you that. Theta maxima of minor lobes is nothing but pattern maxima, and the other one is pattern minima. This is nothing but the null direction. Minima direction of minor lobes, this is also called, or else this is nothing but the null direction. And the last one is beam width of the major lobe. This is nothing but the first null beam width. Along with this, we can also able to get the half power beam width also, because once we get the first null beam width, we can easily find out half power beam width. But what are these four angles that we are actually finding out? The first one is the maxima of major lobe. Second one is the pattern maxima, which is nothing but the maxima of minor lobes. Third one is the null directions or pattern minima. And last one is the beam width. These are all the angles that you have to find out if you really want to draw the radiation pattern of an n element array. Okay, now let us try to assume, okay, this is actually I have taken it before itself. This is the one which will get it for a 4-element array, but I'll be just taking just to explain what are all the angles, right? So theta equal to 0 is the starting point, okay, which is nothing but the antenna array axis. If the elements are like this, okay, if you join all the centers of those antenna elements, you will be getting the array axis along 0 and 180 degrees. And this will be the 90-degree, and this is 270-degree angle, right? Now my point is, as we know that the major lobes, okay, it's very clear that this white line, whatever is showing is the major lobe, okay, major lobe, and this is another major lobe, which are in the directions of 90 and 270. Observe these carefully. Okay, this is along 90 and this is along 270. Okay, so that's what is the directions of maxima of major lobes. Okay, that we have already got it. Okay, and that we have to find out for other problems also. If it is given for an element array which is n equal to 4, we will have to actually find out that. There are several other ways to find out the maxima of major lobes also. Now, if you observe these green lines, okay, these green lines, okay, observe this, okay, this green line, which is immediately adjacent to the major lobe, okay, these are immediate adjacent to the major lobes, are these are the first adjacent lines to the major lobes, in which this line is in between the major lobe and these minor lobes. Okay, this is called minor lobes, right? This is a minor lobe also. Okay, in between this major lobe and minor lobe, you will have a null direction. This is a single direction, single angle direction. This is another single angle direction in which there is no radiation. So these two are the first null directions. Why these are called first null directions? Because these are immediate adjacent to this major lobe. Okay, these are called first nulls. The angle between these two first nulls is called as first null beam width. Okay, so this is what is first null beam width. Observe carefully. And there is another angle which you can able to find out. It looks clumsy, but you have to observe carefully. So this is another half power point directions where the power is half or 1 by root 2 times the maximum value. Maximum is 1 there. And this is another maxima, sorry, half power point direction. The angle between these two half power point directions is called as half power beam width. Okay, so this is HPBW, half power beam width. This also we will be trying to find out. Next, the most important is, this is a minor lobe, and there will be a maxima direction of this minor lobe also. Okay, that is called direction of maxima of minor lobe. There is another direction, okay, for this minor lobe. Okay, this is also maxima of minor lobe. This is also maxima of minor lobes. This is also maxima of minor lobes. Okay, there are 4 maxima directions of these minor lobes, right? Now, once we get these 4 maxima of minor lobes and major lobes and also the first null beam width and half power beam width, it's very easy for us to draw the radiation pattern. If you observe another important point, this is your first null, right? Okay, this is your first null, but after this particular minor lobe there and this particular minor lobe, there will be another null direction. Okay, this is called another null direction, and this is also another null direction. These are called second null directions. Okay, these are called, see, you have to call both of them as second null direction. There will be another null direction also which is adjacent to this. Okay, this is also another null direction for this particular major lobe, but still you cannot call it as a first null. You have to call this is third null directions. There are only three null directions. Okay, don't call this is one null direction and this is second null direction. These two are called first nulls and these two are called second nulls, and these two are called third nulls. Okay, there will be only three null directions. Three null directions. Don't consider them as six null directions. Okay, so that's what we have to find out for the n element array. Okay, whatever I have drawn it for an four element array, the same radiation pattern you will be getting. First thing, even if I call theta maxima of minor, that representation you should understand. Theta maxima of minor means maxima of minor lobes. Theta maxima of major lobes means maxima, major lobe maxima. Okay, and theta minimum of minor lobe means null directions. Okay, these are the first things, basic things that you should understand. Okay, now we'll be moving to the second angle that we are going to find out. You no need to draw that particular diagram, you can directly go ahead. Okay, second one which we have to find out is direction of pattern maxima. You can call it as direction of pattern maxima, or you can also call it as minor lobe maxima. Minor lobe maxima. Maxima of minor lobes. Okay, the representation here is you always keep the maxima inside the bracket and minor lobe is outside. Similarly, minimum is also you keep it inside and minor you write outside. Okay, this is how we should represent that. Okay, so now let us try to find out how to get this direction of pattern maxima. And for n element array, there is only one thing that we know. In the previous derivation, we have derived the most important expression, that is array factor. Okay, array factor will be equal to 1 by n sine n psi by 2 by sine psi by 2, right? Okay, so this is the expression for the array factor. To get the pattern maxima or minor lobe maxima or maxima of the minor lobe, what we have to do is you should equate this numerator part, because numerator will only be considered seriously here. Okay, so numerator part must be equal to plus or minus 1. Okay, and whatever is the theta which is present in this side, okay, that will be giving you the maxima of minor lobe. Okay, so let us now equate that sine n psi by 2, or we can say you can just write a simple statement to get the maxima of minor lobe, equate the numerator part, nr means numerator part of array factor to plus or minus 1, right? Okay, now sine of n psi by 2 is equal to plus or minus 1. Okay, so let us now start with this. Okay, so n psi by 2 will be equal to sine inverse of 1 plus or minus 1. What is sine inverse of plus or minus 1 is? Okay, for what values of sine you will be getting 1 and minus 1, plus 1 and minus 1? It is 90 and minus 90, or 180 plus 90, 270, like that, right? So n psi by 2 is always equal to plus or minus. Here, don't take small n, okay, it is capital N, 2n plus 1 plus or minus into pi by 2. Okay, their capital N is equal to 0, 1, 2, 3, so on. Okay, 0, 1, 2, 3, so on, right? So that's what is your expression. Now you have to simplify this, right? Okay, okay, first n equal to 0 in this will be giving you the direction of maximum, because n equal to 0 will be giving you n equal to capital N is an integer there. Okay, this will be giving you major lobe maximum. Don't consider this because we have already calculated the direction of major lobe maxima. That's what I said. We can find this in several ways. Major lobe maxima you will be getting for the case of n equal to 0. So we should not consider this n equal to 0. We will be start finding, substituting the angles, substituting the values of 1, 2, 3, so on, to get the theta maxima of minor lobes. So that means minor lobes are the secondary lobes. Okay, after major lobes, the next smaller lobes, smaller radiation lobes are called minor lobes. So don't consider n equal to 0 here. You start, okay, from n equal to 1. Okay, that's what you should do it, right? So n psi by 2, n psi by 2 will be equal to plus or minus 2n plus 1 into pi by 2. Okay, don't substitute n equal to 1 now itself. Okay, we'll be doing that for finding out the angles for a particular array, right? So here 2 getting cancelled, and psi will be equal to plus or minus 2n plus 1 into pi by n, pi by n. Okay, so still it is not completed, because psi, what we know is beta d cos theta, beta d cos theta plus alpha. Okay, either you can substitute alpha equal to 0 now itself, or else after sending to the right hand side you can do it. Anything is fine. Plus or minus 2n plus 1 into pi by n. Okay. Okay, don't substitute now. Okay, so in the second next step we'll try to substitute. Put alpha equal to 0. Okay, for broadside array case. Either otherwise you can send alpha to the right hand side and then you can substitute. But for broadside array case, it is clear that alpha equal to 0, right? So beta d into cos of, I have considered theta, which is the maxima of minor lobes. Okay, you can now write that is equal to plus or minus 2n plus 1 into pi by this small n. Okay, here small n is the number of antenna elements and capital N is the integer starting from 0, 1, 2, 3, so on. And what is cos theta of maxima of minor is equal to plus or minus 2n plus 1 into pi by okay, pi by n into that beta d also you send it here. Okay, so this is one way of remembering. Either you stop here or else theta maxima of minor will be equal to cos inverse of plus or minus 2n plus 1 into pi by n beta d. Okay, you can simplify, either you remember like this or else you can simplify like this. Don't substitute small n and capital N also. Okay, just substitute beta equal to 2 pi by lambda. Okay, and d equal to, or else you keep that d as it is. Okay, because you cannot substitute d now, right? So theta maxima of minor will be equal to cos inverse of, what you will get when you substitute this beta equal to 2 pi by lambda, pi getting cancelled. This will now become 2n plus 1 into lambda by 2 beta d. Okay, so this is another way of writing. Okay, because if you remember like this, directly you can take capital N equal to 1 for finding out the angles for a particular value of okay, sorry, this is 2nd, right? Okay, this is because we have substituted the value of beta, so it is 2nd. Okay, so you can substitute n value and you can take d equal to either lambda by 2 or lambda or whatever is the value which is given in the problem. And this we call it as the first equation, right? Now, the third angle that we have to find out is the minima of minor lobes, or null direction. Okay, minima of minor lobes are nothing but null directions, and this is represented by theta minimum of minor. This we have already seen in two element array also. We have equated that cos of pi by 2 cos theta or sine of pi by 2 cos theta is equated to 0 to get the minimum direction or null. In that case, we have to call it as minima. Okay, minima direction, right? But here we have the null directions. Okay, now minima of minor lobes are null directions. We are representing it by theta minima of minor, and for finding this particular angle we have to equate to get the minima of minor lobes equate the numerator part, which we know already, sine n psi by 2 to 0. Okay, so equate that normalized component or numerator of array factor, which we know is sine n psi by 2 to 0. Okay, so this is what is the expression, right? Now n psi by 2 is equal to sine inverse 0, but sine inverse 0 is plus or minus n pi. That is n psi by 2 will be equal to plus or minus n pi. Okay, plus or minus n pi. Now, right. Okay, now this psi is equal to plus or minus 2n pi by n, by small n. But psi will be equal to beta d cos theta plus alpha is equal to plus or minus. It's very easy. Okay, only thing is the number of steps will be more, but the concept is very simple. Okay, here n is actually equal to 0, 1, 2, 3, so on. Okay, now alpha will be equal to 0 for the case of broadside array, because it is broadside array case, right? Then beta d cos theta. Okay, so this cos theta you can call it as minimum of minor lobes. Okay, this is minimum of minor, or simply, okay, don't write theta minimum. Okay, you better call it as minor, is equal to plus or minus 2n pi by n, 2n pi by n, right? Then cos theta minimum of minor is equal to plus or minus 2n pi by n beta d. Okay, now you can write the expression for theta minimum of minor as theta minimum of minor or null direction will be equal to cos inverse of plus or minus 2n pi by n beta d. Okay, either you can remember like this or else beta equal to 2 pi by lambda. Substitute this. Then what you will be getting is theta minimum of minor will be equal to cos inverse of plus or minus 2n pi by n, you write as it is 2 pi by lambda into d. This 2 getting cancelled, pi getting cancelled, and lambda will go up. Then what you will get finally is cos inverse of plus or minus capital N into lambda by n into d. Okay, this is theta minimum of minor. Okay, so you better remember this. Okay, now we have got three angles. If you observe, one is theta maxima of measure. There is no expression for this. Directly we have got these angles as 90 degrees and 270 degrees. And second one is theta maxima of, it's not measure, it's minor now because there will be several minor lobes, and which is cos inverse of plus or minus, you have to remember this, 2n plus 1 into lambda by 2nd. Okay, 2nd. Okay, third is theta minimum of minor, which is nothing but the null direction, is equal to, it is the same cos inverse of plus or minus n lambda by nd. Okay, it's very easy for you to remember. And there will be another angle that you have to find out, which is first null beam width. You will have an expression, you will get an expression for that. From that, you will get half power beam width. Okay, then by taking a particular value of n, let's say n equal to 2, we have already done it. Let's say n equal to 4 and d equal to lambda by 2 case, we will try to find out the radiation pattern for this 4-element array. Okay, because it's going to be very lengthy, I'll be stopping this lecture here. In the continuation lecture to the broadside n-element broadside array case, I'll be finding this broadside first null beam width along with half power beam width, and also I'll do the radiation pattern. I will draw the radiation pattern for a 4-element array. Separation is lambda by 2. Okay, in that what you will do is, you will have to substitute this n equal to 4 and d equal to lambda by 2 and n equal to 1, 2, 3 like that, and here also n equal to 4 and d equal to lambda by 2, and here n equal to z. You will start here from 0, 1, 2 like that. Okay, 0 or I think it's 1, right? Okay, because it's first null direction, you have to take it n equal to 1 only, it's not 0. Okay, so you will have to substitute the capital N integer values and small n equal to the corresponding n-element array, and you will have to find out those angles. Once you get the angles, it's very easy for you to draw the radiation pattern. Okay, so it will be very easy thing once you understand this, and also if you substitute the values, okay, then it will be very easy for us to draw the radiation pattern. Okay, so thank you. I'll continue this lecture, this particular topic in the next lecture. So if you like these videos, please subscribe my channel